are, hold on. I don't want to neglect the fact that there aren't shortcuts, but what I want to make sure you understand is that if I use the shortcuts here, then I fear that those of you who don't have a sense of what this is about lose the ability to understand how the shortcuts are saving you time. So when I say shortcuts, what I mean is this block is experiencing the only unbalanced force in the system. And it is the fact that that unbalanced force will cause the entire system to move that lets me determine the acceleration without really doing hardly any work on the problem. But I'm making a massive assumption when I do that. And that assumption is that these two blocks stay together. But that's the condition I'm trying to preserve. I'm not going to study the condition where that doesn't happen when I'm supposed to be studying a condition where it does. That was an issue for, I think, a few folks in fourth period. So they're like, well, what if it does? I'm like, well, I don't care about that part. That's not the condition I'm trying to meet. I'm assuming there is a condition that exists where the two blocks will slide together. In a few minutes, I had to set it up to help somebody understand this. But even then, it did not get the point across. So instead of doing it that way, where I think we could save quite a bit of time, I'm going to do it the long way. But in the back of my mind, that has to be true. Somewhere, some shape, somehow, that has to be the acceleration of the system if everything accelerates together. Because no matter what, the unbalanced force is the one that was hung, and the inertia of the system is all of the masses combined. That's all there is to it. So if the system accelerates together, that's it. Now, if friction was playing a role, the acceleration would be less by some amount due to friction. And when I say friction, I mean friction between the table and the bottom block. That would be an external force acting on the system. Now, there is friction between the two blocks on the table. That's an internal force. Internal because it acts one way on the top block and a different way on the bottom block. And let's talk about these forces. I'm going to establish that this is my positive direction of motion. Any question about that? So for all of you who are struggling with this, let's go through our set of steps only. There will be a pair of forces acting on the mass that's hung. And that pair of forces is going to be weight downwards and tension upwards, but the tension is going to be less than the weight. Any question about that? All right, good. So those are unbalanced. And due to the fact that they are unbalanced, the net force is going to equal MA, or in this case, mg minus tension equals MA. I don't know tension. I know that that tension force pulls down this way on the pulley, and therefore, if the pulley itself has no mass, which unless you're told it does, you can assume it doesn't, that would suggest that that transfers that tension to the block on top. Let's do that one next. The block on top is experiencing three forces. Tension. I guess it's four forces. Friction. Weight. And normal. I guess I drew that a little bit too high, so you guys can't see it, I guess. There. You see it now? Yeah, there you go. So I think the upward force and downward force are balanced, but I don't think the frictional force and the tension are balanced. Now, this is where I think we got into some problems. Some people believe that these two forces, oops, I want to do that. Go back to where you were. Some people believe that these two forces have to be equal, but that's not true. The box has to accelerate. It's static friction because the box isn't moving with respect to the bottom box, but this force represents the inertia of the bottom box. So we press on with the idea that the net force in the x direction will be tension minus the static frictional force, which will equal ma. And I'm going to need that the net force in the y direction is going to be normal minus weight, and that will equal 0. Because I need the normal force. It's this normal force that causes friction. So I'm going to move on and look at the mass on the 3m box. Sorry, the forces on the 3m box. And although it's probably got lots up and lots down, I don't care about any of those. I just care about the fact that there's one force to the right, the frictional force. There's no friction from the table. So I don't care about the normal force on this box, which is the only thing that would give me. So although there is most definitely a normal force down and it has its own weight down, and there is a big normal force up, none of those forces in the y direction matter. I don't need them for anything. I do need to know that the frictional force equals 3ma. I need that. All right, well, I've got one Newton's law equation that I'm going to need. I've got another Newton's law equation that I'm going to need. And the last Newton's law equation that I'm going to need. Those three equations will give me this acceleration, the acceleration of the system. Substitute into the nucleus. Let me pause right here. Do I need to do the algebra to show that it's going to equal this acceleration? If I do, I'm fine to do it.
Mr.
All right,
Shelton,
that's my name.
why not solve for acceleration with the friction equals 3ma equation?
Because I'll have friction in it.
But what if you substituted friction for mu mg?
Well, you can do all those things. I'm not doing it that way. You can do it that way. You're not saying anything that can't be done. I'm not sure that I'm doing the problem the way you might want to do it. I'm not sure who asked the question, so. Am I good to move on? All right, I'm going to go on. So, let me get rid of this. I don't have an answer to the mysterious voice that asked the question, but my impetus is that you might want to be jumping the shark a bit. Sorry, jumping the gun a bit. We're going to need the acceleration eventually. There's not one of these equations that I can grab that will give us the conditional information we need. We need the acceleration of the system. And the only way to get the acceleration of the system is to eliminate the internal forces within the system. Although it is true that we can bring this to bear, I'm going to use that later so I can preserve the conditionality of the problem. So you do your substitutions. I solve this for t. I put it here. Take this f, put it here, plug it all in, and that gives me this. Promise. Do your algebra. But since no one needs to see that, let's move on. And to me, moving on is to preserve this conditionality. And this conditionality can be preserved by recognizing that I have an expression for the frictional force, 3ma. So I can substitute the 3ma here. using this as the acceleration. And I can substitute normal force here. This will help us preserve the inequality. So I'm going to do those substitutions so I can preserve the inequality and my conditional stay preserved. So friction first. Three MA. And that has to be less than equal to mu, which is given to us, times the normal force, which is just mg. Now, because I used a multiple of the mass, I'm able to get a little bit of a simplification. And I do think it's interesting that this problem does not depend on g. So what I'm left with is m over 4m plus m less than or equal to mu. So it's already solved for mu. You're kind of done with that. What's that? Oh, I forgot my 3. Thank you. Now, if you want to solve for m, you got a little more work to do. I will say the interesting thing is mu shows up exactly where I would expect it to be, on the greater than side of my inequality. Mu must be greater than some value, meaning my surface must be sticky enough for this to work. So I like the fact that it showed up on the greater than side. But to get the actual answer for the mass that you can hang, I've got to do a little more work. 3m less than equal to mu times 4m plus m. Do some distribution, a little bit of algebra, and there you go. This is the inequality.
Mr. Shelton.
There's probably mu on top. Wait a minute. I don't think there's a mu on top. Distribute it. Did I? Hold on, let me make sure I didn't copy it wrong. Distribute it. So 4m mu, yep, there's a mu there. So there's a mu there. There we go. Better. Okay, all better. All right, somebody said something about Mr. Shelton before I realized I made a mistake. I think so too, but I'm not sure. Luke, did you have something to say?
It was for the mistake.
Okay, thanks. I do like the fact that m is on the less than side of my inequality. That makes sense to me. That there's going to be a point where I better keep m less than a certain amount or else it's going to break the friction. Yeah. So I like that it worked out that way. I combined all this because this all has no units in it. So those are all unitless quantities, which leads me to something times m, which does have units in it. And it's units of mass. So I know my units work out well here. So it gives me confidence to think that my calculation has been okay. I also will point out something that it's likely that everything in those parentheses is going to be less than 1. Right? Mu is probably less than 1. And looking at those numbers, I think that's going to give me something that is less than 1. Or at best, relatively small, around 1. Anyways, that was the answer. I don't know where you guys fell on the answer, but that's what it is. So let me probably close, but I know some of you very far away from this, with some people making the wrong assumptions all around. Would anybody like to ask a question about this? Is that your hand up, Ryan? Okay. I just want you to get it above the table. You are an athlete. Thank you.
Mr. Shelton?
Hold on. Ryan's asking a question, and I will definitely repeat it so you know when he's done. Ryan's question is, why can't we use 0 for the acceleration? Because isn't that the threshold? And I think this is a pervasive issue. So I want to be very clear. Let me circle this so you can see. You're trying to say that the block on top does not accelerate with respect to the block on the bottom, right? And that's why you're trying to make these two forces the same. That the fact that the one doesn't accelerate with respect to the other isn't what's being asked. Although that might be true. If we say they both have the same linear acceleration, that's saying the same thing. They both are moving together. So if we try to do it your way, we have to know what the acceleration of the bottom block is as distinct from the top block, and then use a different reference frame to study the top block, one that is accelerating with a different different acceleration than the bottom block. No. I mean, that's just it. The top, I mean, sorry, let me say this, yes. Both blocks have the same acceleration relative to the tabletop, right? So that's what I said. This and this are the same value relative to the tabletop where everything is being compared. You want to make this 0, but it doesn't have an acceleration of 0 relative to the tabletop. It has an acceleration of 0 relative to the other mass that is accelerating. Does that make sense? I think that was something I could not communicate in 4th period. But we are observing this problem as distinct from the system, and we are with the table. We're not moving with respect to the table. We are observing the other objects. And so all of our points of reference are based on that. Okay, so person at home, I don't know who you were.
I was gonna ask, how did you find the acceleration, the mg over 4m plus m?
I found that by eliminating the internal forces from all the forces that were in the horizontal-ish direction. So, I mean, I did not find it that way. I found it by generalizing, but I will first say that I take this and plug it in for F here. And then I need to solve this for T and plug this T in for T here. So if I were to do that, I would get mg minus ma, because this is all T, minus friction, which means minus 3ma equals ma. Now I solve it for A. Good? That okay over there?
Thank you.
Welcome. All right. So, yeah. How did I know to use the friction for the acceleration? You mean, how did I know to use this one? Well, I mean, I didn't use it for the acceleration. I used it because, and if you're asking me, how did I know to use that when I was plugging in earlier to the friction equation? Is that what you mean? It's the only equation here that has just friction in it. I mean, I could have used this one if I wanted to, but I would have had to plug in my expression for tension too to eliminate tension. So when I had friction is less than or equal to mu times the normal force, this is an expression for friction. It's in terms of things that I have. I had A, I had M, and I had 3. I did not have the tension. So I would have had to find the tension, or I would have had to substitute in for the tension, things that have things and I know. Does that make sense? Well, that is not a set of happy faces out there or out there. So I'm going to assume that that's because this didn't work out for you. Sorry. So here's where a teacher says something that will make you guys angry. I told you to look at this one. I said, put the rope on the other box and try the problem again. You know how people ask me about that problem? This many. So, I mean, I made it clear, I thought, that you should expect to see this. But maybe not clear enough. Sorry. I want to see what you did. So I don't know if I'm going to grade this, but it'd be nice to see what kind of mistakes y'all made. I'm pretty sure by looking at your work, I'll know whether you have an idea, no clue, full-blown confusion, or you're really close but made some silly mistakes. So we'll see. I'm a little frustrated about how long this took. So how many minutes till the bell rings? Like not many, right? How did it take up the whole class period? Excellent. I kept trying to tell you I was done waiting for you. I have it set up here in class. We can see it. So for those of you who don't fully appreciate it, hit the lights, please. See it? It's hard for you to see it all the way, but I have a block on the cart. The cart's got like no friction. Got a string here with the weight that I hung. Works, right? If I change it and make the friction less, doesn't. Same idea, right? All right, well, we obviously can't talk any more about this. We've had all the fun we can have. Actually, I'd argue that none of us had very much fun. But hey, you know, it's physics. Who wants fun in physics? So you guys at home, I don't know how much that you're able to see, but we're going to play with it more tomorrow. So I'll have a little bit different setup tomorrow so you can see it easier. And that's all I got. You guys have any questions for me before I say goodbye? Alrighty, bye. It'll be a better day tomorrow, promise. Actually, I can't make that promise. I hope it's a better day tomorrow. So I'll talk to you all soon.